Okay. So in essence, we can categorize machine learning into one of two broad categories, right? We have supervised learning and unsupervised learning. Where in supervised learning, as you might imagine, we're giving the code, the algorithm, more input, right? With unsupervised learning, we're sort of letting the code do its own thing, right? It's a black box in which we feed into it information, and it'll tell us things about the data. What it tells us depends on what sort of framework, what sort of algorithms we're using, but we can talk about that at another time. So because this is an introductory workshop, and I really want to show you the power of data science and what you will be able to do through participating in the High School Big Data Challenge program, this will be very much an exhibition workshop, and we'll just go through like, oh wow, here's some really simple stuff, and this is the power that it can hold, and we'll finish off with the more complicated stuff at a more high level. So just an introduction and analysis of the results. So back to supervised learning. So in principle, right, our inputs into our supervised learning algorithm doesn't necessarily have to be just a number, right? It doesn't have to be like 1, 2, 3, 4. It doesn't have to be 3.14, right? Irrational, rational, what have you. But it can also be other things, right? So like different categories, right? So for example, if you're looking through a bunch of emails, maybe you're interested in identifying what's spam and what's not spam. We can easily run that information through our algorithm and still output valuable information, right? So not just from numbers, but from more qualitative things. And finally, this is more of a nuance at your level, in the sense that, you know, these words ordinal, right, has a particular mathematical meaning and a relevant one in computer science and machine learning, but for our sake, right? So I'm putting myself in the shoes of a high schooler. This, all you need to know is that we can also allow for things that aren't numbers, but also with something that allows like ranking, right? I gave the example here of first, second, and third. So technically, these words here aren't numbers, but we still can categorize them going from one to the next, right? We can order them, ordinal. Anyways, so going forward, there are a couple different ways of doing supervised learning, but we'll look at a couple things: regression and classification. So the idea here is when you have a regression problem, this is where you have a number, right, as the output and input, and you can assign and you can basically get these very, very powerful, robust results based on pure numbers. Classification, as you might imagine, it's where you don't necessarily need a number, and it can be a thing like an ordinal or a category. Yes, so now we're going to start this by going over something that you may have heard about before, right? The least squares method. And that's because the least squares method, or least squares in general, is a statistical concept. And, you know, a lot of people are scared of machine learning because they're like, oh my goodness, it's such a wildly complicated thing. It must be. It has the word learning and machines in it. But in reality, if you break it down, it all becomes statistics at the end of the day. And, you know, this makes a lot of science enthusiasts unhappy because it sounds more boring that way. But at the end of the day, it is actually a really, really simple concept that anyone can use in order to improve their results, or at the very least probe their results. So in principle, the least squares method, we take the difference of some hypothesis and our input, right, our data point, and we try to minimize this value here. And, you know, some people like might see this and go, oh, it's the sum. Oops, ignore that. Some people might go, there we go. It is the sum, or the sum of all of the square differences between some hypothesis, something, and a data point. And they're like, wait a minute, that looks an awful lot like variance, or an awful lot like standard deviation. And that's actually a really good way of thinking about it, because effectively what this gives you, what this squared error cost function, what this thing here gives you, is a measure of like how far away from the best or the true it really is. So we can go further into this and say like, okay, well, I have my data points which I know for sure. This is just data, this is facts. But what about my hypothesis, right? I know that if I'm doing like stats, right, really basic stats, taking averages, stuff like that, this thing here is just the mean, because we want to find the difference from the mean. Well, for us, we want to find the difference from, we want to find the difference from the best sort of function, the best sort of result that we can get from our data, right? So our program, our code, will basically use this as the basis, right, of determining the best hypothesis. So this plot over here just goes to show what I was talking about, right? So in principle, right, if we had a line that went straight across, there'd be huge, huge, huge differences, right, between the line that was plotted and the actual data points. But as we continue to sort of optimize this, right, to minimize this error cost function, what the algorithm will do, it's like, okay, well, very clearly a horizontal line doesn't fit this data very well, and it will continue trying to fit it until it looks nicer, right? Both qualitatively to our eyes and quantitatively based on this squared error cost algorithm thing over here. But like at a high level, that seems really easy. But how do we actually code this? How do we actually deal with it, right? How do we define the steps in which we take to get from something that doesn't look nice to something that fits really, really well to the data? Well, then we can talk about some different fun things like gradient descent. And gradient descent is probably one of those buzzwords that you've heard a lot, and you may not know necessarily what that means. But in principle, right, gradient descent is the way to find a quick path to the optimal value, right? So a quick path to the minimum value of our squared error cost function over here. And at a high level, right, basically we have one variable, right, one little input, and we say, okay, well, we're gonna see how fast our error cost function, this thing over here, changes. That's what this derivative here means. So we're taking a look at how fast this thing changes, and then we multiply it by alpha over here, where alpha is the learning rate. And in principle, this alpha here itself can be changed and tweaked based on the needs of the data scientist or the person doing it, right? And there are a lot of reasons why you should tweak this, or even how to tweak this, but those are a little bit more mathematical and less intuitive at our level. But at the end of the day, all you need to know is we have like some value, and then we subtract off some parameter, some value, based on how fast our error function changes. And the idea is we run through this iteratively until we get to the minimum value, right, of this error function, and we get the best fit line. So again, just to summarize at the high level, we have an error function, something that measures how far away you are from the best fit. And then we have a way about which we can minimize that quantitatively and iteratively. Iteratively means like you do it once and then again and again and again and again and again until you get to the best sort of fit, right? And by converge, I mean you want to reduce it until it gets really, 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 really hard to reduce anymore, and you basically can't tell the difference between one step and the next step. All right. So now we can get into logistic regression, right? Where now we can actually sort of define our hypothesis, right? That I mentioned above. And oh, hang on a second. This needs to be fixed. That should look a little bit nicer. This is actually just a typo. You don't need to worry about this. Perfect. Great. All right. Now things look nice. Sorry about that. Okay. So like I was saying, now we can actually sort of define this this hypothesis in some sort of quantitative way, right? Because before it was just like, well, it was just a letter. It was just some function, but I didn't say what it was. Well, now what we can do is we can assign it some function. Here it's a sigmoid function given by this formula here. Basically, all you need to know is that the function that we're doing can be taken as the fraction of 1 plus e to the minus z, where this thing over here is basically just saying that z is a real number, right? So that can be 1, it can be -3, it can be like 0.05, et cetera, et cetera. So our hypothesis function, our little function here, takes the following form. And basically, let's say that we stick a number into this function and then it spits out a number, right? And it'll give us, for example, 0.7. And that basically means that we have a 70% chance of a positive outcome. So the idea here is we've defined our hypothesis with some probabilistic interpretation. And using this, we can assign, or going forward after this step over here, we can basically say, okay, well, now I have some function, some hypothesis, and if I go above or below some boundary, I can make decisions based on that. But that's still really simple, and honestly, it might make things a little bit complicated if you don't understand like the probabilistic interpretation. But there are ways to sort of improve this, right? And now we can take a look at our cost function. And basically, our cost function is another sort of so the same cost function as before, but the idea here is that instead of the difference of squares, we can define it in another way such that we can deal with data in a more robust way. So for example, let's say that we input some value into one of these functions, right? And then it spits out another number. Well, once we spit out a number, then that'll tell us how cost effective it is, right? And there are different ways to define cost functions. In principle, you can define a cost function where you want to sort of minimize this, and the output and we would call this a cost function. The value that you get is the cost to do this step. Now, of course, cost is something that we want to minimize, and that's the main idea here, right? Until we minimize it enough that we get the optimal value. Some cost functions, right, actually want to be maximized. And in these cases, the number that's spat out is called a reward. And we want to maximize the reward because, well, we like rewards just in general. But the difference between these two things just depends on your problem. And for our purposes, we're just going to focus on a simple cost function and try to minimize this thing over here. So now we can define now we can go through our gradient descent, specifically for this whole logistic regression. So once again, we have our little cost function here that takes into account everything I said before, right? So our total cost function takes this form where we have our hypothesis, our values, it does some mathematical operation, and basically we want to try to find the minimum of this value here. So we keep running this thing over here iteratively. So that means we run it once, and then again, and then again, and then again, and again, and again, and again, until we get a minimized cost function, right? And yeah, at the high level, that is all we really need to know. And now we can get to the code itself, because the code is actually really, really easy to understand even at this level. So first, we can begin off by importing our required Python modules. So basically, this code block here is saying, okay, well, I need, like, right now I have a sandbox, but I have nothing inside of that sandbox. Well, let's bring some tools, some toys into that sandbox. Pandas and NumPy are basically just a way of getting mathematical operations. You can think of it that way. This thing here, matplotlib.pyplot, that is a plotting library, right? So it allows us to plot things. Random basically generates random numbers. SciPy, again, like Pandas and Numpy, it just gives us more mathematical tools to work with. These things over here, so this is a machine, like basically these gives us our machine learning tools, right? So we have our linear regression and a whole bunch of other functions that you don't necessarily need to know at this level, but just understand that they can give us the important things that we want. So I also see that there was another question asked, and I'll actually answer this one right now. So how do we optimize the original hypothesis function depending on what the cost function outputs? So going back quickly, the idea here is we can take the sort of rate, right, at the rate at which our cost function changes, because again we're running this iteratively, and try to take and basically subtract off the non-optimal part of it and then run it again. That will spit out another number, and then again it's like, okay, well now the cost has been minimized, but maybe not enough, so we can run it. So then we can take the difference between what we got and the non-optimal part, run it again until we converge into a proper minimized value. And we'll get into this further down here. So yes, like I was saying, we're going to import these modules. You can press this little play button here or hit return, shift return. It'll run that. This line here is basically just for this notebook. It's saying that we can plot things in a way that we can see them. We don't have to open up any other files. All right, cool. So now we're going to give an example. Okay, so we need to create some random data, right? And we're going to assign things, we're going to assign the data labels. And those labels will be 1 or 0, right? Heads or tails is what I'll call them, depending on which side of this line they fall onto. If they're above, we'll call it a, or sorry, if they're below, we'll call it a heads. If they're above, we'll call it a tails. So we need to train our model, right? So this is what our code does to sort of optimize, right? So to minimize that cost function. And then the rest will be test data, because at that point we won't be learning, we won't be minimizing that cost function. We just want to try to apply this model to a data set and see if we can get, like, good results, basically. So here we're just using a small set of samples, right? So a small number of random values, really only because we're doing this for learning purposes, right? In principle, you'd want to have a lot of samples, right? A lot of samples, because the more data you have, the stronger your machine learning model will be. And there's a caveat to this, in that if we can overtrain our model, but for our purposes right now, let's not worry about that. We're going to take our samples, our 50 samples, and then split them in half. We're going to train with half of them and then test with the other half. In the real world, we don't have like a ton of data. And because of that, what we want to do is we want to train it on as much data as possible and then try to apply it to actual test data. So here, we're going to take about, we'll take 50-50, but in the real world, maybe you want to do 80-20, 70-30, even 60-40, just depending on your needs. So let's create the data, right? N equals 50. I'm just saying how many samples we're going to have. This will create a random, or this will define the seed, right? Random seed. And next, I begin by, I begin by making a bunch of random points. So let's do that. We do that, And now we're like, okay, now let's look at the data that I made, right? And here I'm literally just taking the data set and I'm looking through the first 5 values. And the way that Python runs is that you go, or you do your arrays from 0, and then when you're looking at things, you go to the last number where the last number is not inclusive. So in simple language, we have the 0th point, the 1st point, the 2nd point, the 3rd point, and the 4th point. It's 5 points total. So here we take a look, and yeah, these look pretty random. All right, cool. So now what we can do is we can do the same thing with the training data over here, right? So let me run this thing, and I'll run that one. Cool. So now we can begin to do our logistic regression. So what's nice about Python, and for your work, for the competition, for anything really, is there's been a lot of work already done to build these libraries of codes and functions that you can use yourself without even having to write them yourself. And that's what we're going to do at this level, because, well, this is an introductory workshop, and this is to sort of show you what you will be able to do at the end of it. And I want to really, the end of the High School Big Data Challenge, and I want to really put into your minds that at the end of the day, you will learn how to do all of this, and there are a lot of already pre-written functions for you to be able to utilize and use. So let's do that. And basically what's happening here is we are beginning to run our logistic regression, right? So here, like again, we define what we're running, and we fit them, and then it spits out some set of parameters. Okay, so it does that. Next, let's say that we want to see the results of what was run. Well, we can call those things, and we'll do exactly that. So this gives us the slope, the intercept, and effectively like some scaling parameters. Okay, so now we have our logistic regression in order. Let's start using our actual training data. Well, the nice thing about training data, like we said, is we want to be able to see like whether or not our model, like, one, works, right? And two, if we can apply that model to other things and be like, oh wow, this model that we trained on data, this model that used data to learn, can also be applied to other data. So let's get started with that training step. So again, we already did our regression here, and now all we want to do is see the results, because here I know that it ran, but I don't know what the heck any of these numbers mean. I want to put this in a way that like I can read, I can see and understand. So let's plot that. Here, the first line is we're saying we're going to plot a figure, and this is going to be the size of the figure. Then we're going to take we're going to define one of the y values that we're going to be plotting. We're going to tell it what those y values are. Here, it'll be the predicted training values, right? Then what we're going to do is we're going to do a similar thing, and we're going to actually plot the data points. So this part over here is going to be plotting a line. These parts here are going to be training the actual data. Or sorry, these parts are going to be plotting the actual data. Here, we're giving them labels. Now here, because we already know, right? We already know what the function will actually do, because again, because we define the proper function, the function that we're trying to learn. We can be like, okay, let's compare that to what the machine learning model spits out. So we do that, plot everything. We can assign labels accordingly, and let's see what happens. Well, we run it, and now we have a plot. So again, at the high level, what we did was we created some random data. We verified that it was, or we looked to see that it was random to our eye. We ran the logistic regression, which was already predefined by some ready libraries, and then we trained the data, right, and plotted it. So we trained the data, we plotted it, and now we ended up with this nice little plot here. So our plot here is saying, okay, with the random data, I have a bunch up here and a bunch down here. And like I mentioned, tails will fall below the true plane, right? So the actual function. And then we have the red data, which is tails, which will fall above the actual function. And this orange line here, this orange line, that is what our machine learning model predicted. So basically, it saw this data. We gave it these sorts of labels, right, as either heads or tails. And then the machine learning model was like, okay, well, I see that there's a whole bunch of heads or tails over here and a whole bunch of heads over here. And then let me try to run some logistic regression to sort of find the line through which we can demarcate, we can separate these two. And this is what our machine learning model gave us, this orange line here. And you know, like for the purposes of this data, it looks, well, it's exactly correct, right? It's like, oh wow, oh my goodness, wow, look, it separated them perfectly. But there is some deviation between the true plane, right, the actual function, and our machine model plane, sorry, machine learning model plane. And in principle, you know, this is an algorithm at the end of the day, and there are ways to improve this, right? So we could train it on more data until we get the actual sample itself. And if we wanted to, we could simply switch out this number here. Instead of 50, it could be like 500,000 or something like that, until we get something good. So that's what we can get out of this plot, right? All it took were a few lines of code in order to, you know, do machine learning. But you know, this was training. This was training. What about looking at the rest of the data that we didn't train with? Well, we can do the exact same thing, right? So we define our plots and so on and so forth, right? We take the results of the machine learning model from before, right, and compare and see exactly what we get. So once again, right, this one, right, so the green will give us the true plane defined by the function that we started out with, right? C will be using the machine learning model results. So let's do that. Let's see what happens. So, oh right, I should probably run it. So we run it, it does its thing, and it's like, oh my goodness, wow, we get a pretty plot once again. So let's take a quick look at it, and we notice first of all that we get some similar results, right? But now, if we look at where all of the heads lie, they're still, you know, broadly speaking, below this area, right? But we know that above this line, again, broadly speaking, they're still all tails. So that's good. That's good. But let's compare the lines now. So we see that our true plane over here, right? It works like, again, it's going to do what it does. But the issue is now we have some errors over here. And this one should actually be classified as a tails. However, using our machine learning model, right, this is saying that we still have our tails up here, we still have our heads down here, and this falls below this line. And this is because, right, the reason that this is like miscategorized is because our model wasn't, well, it's not 100% right. Well, we are still able to do a really, really good job of separating these two things between what falls above and below this line, or the line that we defined. So here, I'm just I'm just describing exactly what I said, right? And the ways to sort of improve this model in practice would be to assign more training data, and well, really that's it. This is a simple way, and we try to fit the data based on way more sample points, right? As you might expect, the more data we have, the better our model will be. But I mentioned that there's a caveat here, and the caveat here is that we can overfit our model. And what that means is that if we train it with too much data, like too much data over here, we can overfit the model. And what happens is that it won't be it'll basically only work for that set of data, and it can give us incorrect results. So there is a sweet spot between having not enough points and too many points that you want to try to reach in the real world when you're doing this. So I gave some notes from a course here that you can take a look at in case this boiled down version was not enough. This course will be more technically heavy, but if you're keen and interested in learning the math, I'd recommend taking a look at this. So once again, just to summarize, what we did was create some random data. Then we're like, okay, now let us run our logistic regression model, where we have some cost function that we try to minimize. We do that a whole bunch of times until the machine learning model is like, okay, I think I have a good idea of what is happening. And then we plot our results, and we're like, oh my goodness, look, we trained the data, it works really well. Let's look at some real data. Oh, it still works pretty well, but there's some error that we got to fix by using more data points, but not too many data points. So that is the whole supervised learning thing. And again, I understand that this may be complicated and complex, but this is just to sort of showcase the things that you can do. And remember, this is all done in less than 100 lines of code, right? Probably not even 50 lines of code, which is phenomenal, considering that when you're designing software or doing more robust things, you can have thousands of lines of code. So now I'm going to stop sharing this screen, and we are running short on time. So what I'm going to do is I'm going to very quickly cover the results of the unsupervised learning, and then I will take the time to answer any and all questions that you have about, well, really anything machine learning related, anything related to these modules, and finally, anything related to the competition. So let me share my next tab over here. Unsupervised learning. So we covered supervised learning, and that we have the inputs and the outputs, and we're like, okay, machine learning model, do your thing. Give me a model where we can give me a model that can be applied to more data that I didn't give to you. Now, what if we only have inputs, right? What if the situation is we have a lot of data, and we wanna understand stuff about it, but we don't necessarily know the well, we don't necessarily know how to do that mapping, right? And we don't know what to output. Then we can use unsupervised learning, but this tends to be a more complicated thing to do in principle. But we will rely on well, I'm going to give you a very high-level overview, and we're going to interpret some results after running the code. So here, some examples that we give are clustering, which is exactly what it sounds like. It tries to cluster data, right, based on how similar they are with different parameters, right, with different categories. Then we could also do dimensionality reduction, which is a fancy way of saying we have a ton of data, and we only want the we want to reduce it down to the most essential parts where we can still predict and apply that to other things. And this is really useful, right? Because if I give you the choice of reading 100,000 papers versus reading 10 papers, you'd probably choose reading 10 papers. So in this, we're going to cover both of those things. But at the high level, I really want to cover, well, I guess with the time remaining, all we can really do is take a look at the results. But here, the idea that I want to give is that we can take this problem of reducing down the dimensionality and do it once again in a way where we can like easily optimize and reduce like something, right? Here we can define things in terms of what's called principal component analysis. Here I give an idea of like, okay, we have like a whole bunch of data, but we can instead of having, instead of plotting this data in n dimensions, right? Like let's say we have like 100,000 points, instead of doing 100,000 dimensions of plotting, which I can't visualize. If you can visualize it, that's awesome, but I can't. I'm not good enough for that. So I'm going to try to be clever about it, or I'm going to try to be simple about it and plot it in a different way. And what we can do is plot it in this sort of 2D way, and stick all the points and define what they are, basically based on Euclidean distances, right? So distances. Next, I define here what principal component analysis is, and the idea here is that we take a whole bunch of data, right? Then we run it through some sort of mathematical formula, which is given here. And basically, this weights the data based on like certain principles. Here next, we define something that can be maximized or minimized, right? Just depending on what we want to do specifically. Once we have that new variable, right? We will use that variable to test back and be like, okay, well, I don't really care about this other data based on this thing over here. Let me get rid of that, and then we can repeat, so on and so forth. And really, like, you can do this a whole bunch of times, right? To get all of your principal components, right? So these variables here will be your principal components. But for the purposes of this module, we're just gonna take a look at two principal components and see where that gets us. So again, running low on time, all you need to know is that we import our libraries like before. And what we're gonna do is we're gonna look at some breast cancer data. So, when you're looking at tumors, right, or rather moles or what have you, if you're doing like skin cancer or really anything. But when you're looking at tumors, you're interested in a couple things, right? Their shape, their size, and changes in time, right? Like how splotchy they are, stuff like that. And doctors do this, and they can stick and they can write that data down. And what we can try to do using the power of machine learning is try to sort of categorize these things and see if we can learn more about all of this data, right? And sort of break it down into the principal components, right? So instead of having like a whole bunch of parameters, we can reduce it down to just like the bare basics and see if we can get any information out of that. So we import all of our libraries. Done. Cool. So now data, this is basically just saying, oh, let's see how much data we have. Okay, cool, right? So we have 30 features to look at. Well, what are those 30 features? I don't know, and how many data points are in each of those feature categories? Well, we have 569 for each of those 30 categories. So let's take a look at some of that data. And now we run our little data frame here, right? And we're like, okay, well now Python is now our code is like running through this, and it's like, oh wow, oh my goodness. Well, we looked at the data. Now for us, let's look at it with our eyes. So here we have a whole heck of a bunch of categories, right? So like I was talking about, the radius, texture, perimeter, and so on and so forth. And we can continue with other sort of features, other data sets, and so on and so forth. So here I loaded the first 15, radius, all this stuff. Let's look at the other ones. Oh, compactness, error, and so on and so forth. And now we've loaded the data, and now what we want to do is we want to actually start examining this data. And once again, running very low on time, so I'm just going to speed right through this. We look at the data, we run it. Basically, we're plotting a histogram, and what this histogram is doing is it's taking all of this tabulated data, and it's like, okay, how many times is the mean radius like somewhere in this region? And it's like, oh, like this many times. How many times is it in this region? Oh, it's only like about 30, 35 times. And you know, this isn't normalized, which means it's not scaled. And in order for us to work with this, we need to, well, scale the data into a workable form. And basically, using some of the libraries that we loaded, we can scale it. We do exactly that. And oh yeah, let's plot that now. Once we plot it, right, now things are scaled and moved in a very nice way, right? So we have now the histogram is zeroed on some value, and we've done that for every single one really, really quickly. And now we can start going a little bit forward, a little bit quicker. And basically here is we're finding some more statistical data, basically. And this will be used in our calculations. All right, cool. So now I'm gonna run through this and run through this and run through this. Basically, all this is doing is it's giving it's saying which tumors were malignant and which ones were benign, which ones were found to be that way. And this will not be used in any of our calculations, but this is going to prove a really, really cool point in just a second. So again, before we had all of this data, which we scaled and looked at, right? And then now for us, because we're sort of verifying this sort of thing, we're going to be like, okay, well, which tumor is malignant, which one's benign, which one's dangerous, which one's not. But the machine learning model won't know anything about that. That's just us. That's just us. So now we can do the actual principal component analysis. We run that, right? And again, all of these are really, really easy things that were just simply taken from libraries that people have written before. Okay, cool. So now this is basically just showing like the variance, right? So how far away it is from like a good, basically, for each principal component, right? And again, there are a bunch here, but for our purposes, we're only going to look at a couple. So again, just now again, running really low on time, unfortunately, but I really, really want to get to the point of showing you these really, really pretty plots. So the first one I want to show you is a little bit further up, a little bit further up. Okay, this thing here. So basically, what this is saying is we had all of our categories, all of these things over here, right? And then the machine learning model, right? It ran through all of these things, and then it defined them into, and we're taking a look at some principal components. And basically, what this is saying is like, okay, well, I know how correlated this component was with radius, with compactness, whatever. I can see how correlated they were with principal component 1 with all of these things, 2 with all of these things. Basically, this is a pretty way for you to show your data that will make people go like, oh wow, colors, this is awesome. But maybe we want to actually have something more quantitative, right? Here I'm just giving more values for each principal component. But what I want to show you now is the really, really, really exciting part. This is just tabulated data for each principal component. The really, 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 really exciting data, which we're just about to get to here. And perfect. Okay. So basically, what's happening is we're plotting one principal component against another, right? And we're going, okay, well, our machine learning algorithm output all of these values which I showed above, right? We can do a color map, right? That tells us like how correlated they are with each data point, et cetera, et cetera. And then we've plotted it now. But what I want to show you is, I said that this machine learning model, right? It spat out these numbers, right, for each principal component. Each of these data points corresponds to effectively a different tumor. Okay. All right. Cool. And I said before that like us as the learners here, already know which ones are malignant and which ones are benign, right? Which ones are dangerous and which ones are not dangerous. Our machine learning model does not know that. But what does our machine learning model say if we overlap what we know with what they've plotted? So we're going to do exactly that. And we'll see, once this loads, is that even though we didn't tell it what a benign tumor was, we didn't tell it what a malignant tumor was, it was able to split them up, right? Just based on this principal component analysis into what was benign and what was malignant, all by itself. We just fed it some data, we helped scale it, right? And then it was like, okay, I got this. Let me categorize these things into these principal components. And then when we plot those principal components, we can see very clearly that there is a very, very distinct separation between benign and malignant tumors. So I don't know, that was extremely exciting for me, because it's like, wow, we took all this data, right, and we were able to use this machine learning model in order to separate these things. But we also had other principal components, right? PC1, PC2 over here, and it didn't separate it. So it is up to us as the data scientists, the machine learning experts, to be like, okay, which principal components will give us some valuable results? And here, this is in our case, we were like, oh, this is great. PC1, PC0. If we plot those, we get a very, very distinct categorization between benign and malignant. And unfortunately, we're running very, very low on time. And now I'll turn back to questions. So thank you all for sticking around. And yeah, if you have any questions, feel free to ask them in the chat. Once again, this workshop was very much a way to showcase the power of machine learning, right? Rather than necessarily having you be able to run these steps one by one. And the whole point of this workshop was to show you exactly what you will be able to do, right? This is the hardest it's ever going to get within this competition. But we've designed a bunch of learning modules, plans, and workshops in order to get you up to this step, right? We're going to bring you up to the ability to be able to do these things. And as we saw, all we really needed to do was call a few libraries, stick some data into them, and then spit it out. And then the interpretations that were done were up to us as a scientist to talk about. So, any questions whatsoever? All right, so I'll give it a few minutes, of course, right? Where do we get the data sets for the competition? Great question. So we will be providing to you a series of data that you can, that you'll be able to use, and we've curated this data for you specifically around more demographic and education related data. So we will be providing to you these data sets. However, we will be strongly encouraging you to also be looking for open data, and we will provide sources for you to look for this open data. For example, the government websites provide a ton of freely available data. And all you really need to do is just click a link and download it, and we'll show you exactly where to do these things. So yeah, thank you for that question. And of course, if you're really keen and you want to collect data yourself, you can do that too. For example, what you can do is you can take social media data, right, and take a look at what things were said, how many times they were said, and use that data yourself. So sources of data, we'll provide them to you. You can find open data on government websites, for example, or third, you can collect the data yourselves. And since there's time between people asking questions, I wanna make the note that, again, going to this competition, we're assuming that no one will have any programming or data science background at all. We will be teaching you from the very, very bare basics, the bare bones, getting you all the way up to the point where you can do this sort of thing. Here, I used some examples that were in the supervised learning. I used the example of something very abstract, right? What's above a line, what's below a line to do that. With the unsupervised learning, I use medical data, right? So tumor data. Here we'll be doing education-related data, but the idea that I want to get across is that these things here, right? All the code I written, all the code that we wrote, it didn't care about what was medical, what was math. It just cared that there was data. And it's really, really easy for us to be able to do similar sorts of things with educational, demographic data, et cetera, et cetera. For example, maybe we want to take a look at demographic data of students, right? And their test scores, for example, based on their families, like their family's wealth, right? And then we can be like, okay, well, let's see how many students' scores fall above this line dictated by their familial wealth, right? And then how many students fall below a particular threshold. And then we can go, okay, well, if they have this much money, right, or if they come from a better off place, they tended to do better, for example. Well, maybe that, and then once we have that information, what we can say as the interpreters, the scientists, we can be like, okay, well, maybe this is because those that come off from wealthier backgrounds have better access to educational resources. And then we can, like us as competitors, can try to design or suggest ways to sort of combat this, right? Right. Any other questions? Well, the other thing is I very much am keen on helping, well, really anyone that comes and asks for it, right? And if you can't think of a question now, but one pops up later on, feel free to shoot me an email, and I'd be more than happy to answer for you. It can be about anything, whether it's related to the competition, to the machine learning modules we used, suggestions for learning resources and learning how to code, on learning how to do basic stats, stuff like that. When do we get the data set? Is it after we register? So the data sets will be provided to you, the ones that we provide it to you effectively soon after the registration deadline ends. So the current plan is to provide you with a welcome package that will give you instructions, right, as well as data sets. Then once the competition begins more formally, then we'll be providing to you even more data and information. So in short, when you'll get the data set is after the registration deadline ends, basically the day after. All right, there's about 3 minutes left. I'll stay online until then. But for the current purposes, we can bring this to a close. Right. I suppose I can talk about the competition a little bit itself. So we're also procuring mentors who will be able to provide guidance and help with this sort of thing as the months progress. And these experts are people with actual proper data science background, proper software design background, as well as backgrounds in education and academia in general. So this was actually an interesting competition for us, because in the past, when we did more medical themed competitions, it was really easy to get doctors, health scientists, stuff like that. Now we're focusing more on social scientists, right, as well as the data scientists proper. And it was really interesting in communicating between the health scientists, the doctors, compared to the social scientists. The health scientists were actually tended to be way more formal than the social scientists were. I don't know. I thought that was a really fun quirk. And with the social scientists, it felt easier to talk to them. And I really hope that will transfer to the competition itself. So don't be intimidated by knowing that there are, you know, like scientists and professional programmers there. But again, this competition is designed to help you learn, designed to help you network, and so on and so forth. Okay. All right. It seems that's pretty much it. You know, if you have any questions in the meantime, feel free to shoot me an email. If not, it was great having you, and I hope you can see the power of what you will be able to do. Like, I'd say guaranteed, but you know, maybe you quit after the first week, and because you got bored. So if you stick through it, I can pretty much guarantee that you'll be able to do all these sorts of things that I just showed you, and we'll provide to you a whole bunch of learning modules in order to make the process way easier for you. So yeah, with that, I'll be signing off, and I hope everyone has a fantastic afternoon. All right, bye everyone, and hope to see you during the competition.